Personnel health and safety consequences in SIL determination, prioritizing human impact in IPF classification. When assessing the need for an instrument protective function IPF, consequences to personnel health and safety are considered the highest priority. Unlike asset or environmental impacts, risks to human life carry the lowest tolerance thresholds and directly influence the minimum required safety integrity level, SIL. Even when the probability of a hazardous event is low, the potential for fatality or serious injury mandates a conservative, protection-driven approach. In such cases, the IPF must be designed to minimize the probability of failure on demand to a justifiable and demonstrable level. Severity classification for personnel safety. Consequence severity to human health is typically classified into defined tiers, ensuring that SIL assessments follow a consistent and traceable standard. Negligible, no injury or health effect. Example, non-toxic release, low temperature steam vent, no exposure risk. Minor, reversible health impact, first aid treatment sufficient. Example, brief exposure to low-level irritants or noise beyond comfort threshold. Moderate, lost time injury or short-term hospitalization. Example, exposure to moderate heat, pressure release, or chemical irritant with recovery. Major, permanent injury or fatality of one person. Example, failure leading to high-pressure gas release, localized explosion, or fire. Catastrophic, multiple fatalities or significant long-term health consequences. Example, large-scale toxic gas release, full unit explosion, structural collapse. These categories must be assessed based on credible worst-case outcomes, not average or expected scenarios. The presence of mitigation, e.g. PPE, evacuation plans, may reduce frequency, but should not downgrade the consequence classification unless proven fully effective under failure conditions. Influence on SIL assignment. Personnel safety consequences drive the assignment of higher SIL targets, often requiring SIL-2 for single fatality credible risks, SIL-3 for multiple fatality or high exposure scenarios, SIL-1 only when mitigated consequences are minor and fully documented. The higher the consequence, the lower the allowable PFD and the greater the scrutiny on design, verification, and testing of the IPF. Regulatory and corporate implications. In many jurisdictions, protection of personnel is governed by strict legal frameworks, e.g. OSHA, COME, Seveso Directive. As such, risk tolerability thresholds are often externally imposed. SIL justifications must be documented for regulatory review. IPFs tied to personnel protection typically undergo more frequent audits and tighter change control. Conclusion: safety consequences define minimum protection requirements. Personnel health and safety considerations sit at the core of IPF classification. So the potential for injury or fatality elevates the SIL requirements, reduces tolerance for failure, and demands greater design rigor. By accurately classifying these consequences, engineers ensure that protective systems are aligned with their most critical function, preserving human life under all credible conditions. Economic consequences in SIL determination. Aligning IPF design with financial risk exposure. Economic consequences represent the potential financial impact of a hazardous event if an instrument protective function IPF fails to act. These impacts may include equipment damage, production loss, extended downtime, and recovery costs. While economic risks do not carry the same life-critical urgency as personnel safety, they often justify the need for protective instrumentation, especially in high-throughput or capital-intensive facilities. The classification of economic consequences enables organizations to balance safety investment with business continuity objectives, ensuring that SIL targets reflect not just hazard severity, but financial exposure as well. Severity classification for economic impact. Economic consequences are typically grouped into defined levels to support consistent SIL assessments. These levels consider both direct costs, e.g. repair lost product, and indirect costs, e.g. restart time, contract penalties. Negligible, minimal cost impact. Minor nuisance, example, small process upset, short restart, low value product loss. Low, localized equipment damage, short interruption. Example, minor pump damage, piping stress requiring inspection and recommissioning. Moderate, damage to major equipment, several hours to days of downtime. Example, compressor failure, distillation column upset, raw material reprocessing. High, significant asset damage, prolonged unit outage or replacement. Example, fired heater, reactor, or major rotating machinery loss. Catastrophic, total asset loss, plant-wide shutdown, or multi-million-dollar impact. Example, explosion, full unit rebuild, or long-term production contract breach. These categories are evaluated based on the credible worst-case outcome without IPF intervention. For facilities with high product value or tight production margins, even short disruptions may warrant protection layers with elevated integrity levels. Economic risk and SIL allocation. While safety-driven CL targets often default to conservative levels, economic-driven CL requirements allow for more nuanced trade-offs. SIL-1 may be sufficient where downtime is tolerable and recovery is straightforward. SIL-2 may be justified where financial exposure exceeds acceptable thresholds or insurance coverage mandates higher reliability. SIL-3 is rarely assigned based on economics alone but may apply to ultra-high-value processes or proprietary assets. Insurance, stakeholder, and market considerations. Beyond direct cost recovery, economic consequences may affect contractual obligations and penalties for missed deliveries, reputation among customers, investors, or regulators, insurance premiums and policy terms, especially for repeated loss events. In such cases, the justification for IPF design integrity extends beyond operations and into the financial risk management domain. Conclusion: financial consequence as a driver for protection strategy. Though economic loss may not pose immediate harm to people or the environment, it remains a vital input in SCL determination. Proper classification of economic consequences helps organizations make informed decisions about risk acceptance, investment in redundancy, and overall system resilience. A strong economic rationale supports business continuity while reinforcing the credibility of safety instrumentation planning. Synergetic consequences in CL determination. Understanding compound risk and protective function assessment. Synergetic consequences arise when multiple individual consequence categories, such as safety, environmental, and economic, interact or occur simultaneously due to a single failure event. These compound outcomes often create a risk profile more severe than the sum of their individual parts, justifying higher levels of protection in Instrument Protective Function IPF design. Traditional SEAL assessments typically evaluate each consequence category in isolation. However, synergetic consequences acknowledge real-world complexity, where a process deviation might simultaneously injure personnel, release hazardous materials, and damage high-value assets. Typical characteristics of synergetic consequences. Synergetic scenarios often involve cascading failures. An equipment failure triggers a chemical release, which in turn causes a fire or toxic exposure. Multi-domain impacts. A single valve malfunction results in environmental contamination, major financial loss, and potential regulatory enforcement. Aggravated public or reputational damage. A minor incident escalates due to poor containment, delayed response, or overlapping system failures, attracting legal, social, or political consequences. Examples of synergetic consequence events. Loss of containment in a toxic unit. Causes personnel exposure, safety, off-site release, environmental, and prolonged downtime economic. Compressor failure in a flammable service. Leads to a gas cloud ignition, damaging nearby units and triggering evacuation. Reactor runaway during startup. Results in both internal damage and venting of unburned feedstock to the atmosphere. Implications for SIL assignment. When synergetic consequences are credible, the highest individual consequence category typically governs the SIL target, but the combined impact may justify moving to the next SIL level. Standard risk matrices may underrepresent the compound nature of the event unless configured to flag synergetic outcomes explicitly. Conservative assumptions must be applied to capture the potential for escalation and reduced operator response time under complex, multi-hazard scenarios. Design and verification strategies. To account for synergetic risk, IPF planning should include integrated hazard analysis methods, e.g. scenario-based HAZOPs, scenario mapping that illustrates how single failures can lead to multi-consequence events, CL verification models that incorporate adjusted consequence severity or frequency factors. Where IPFs are shared across domains, e.g. a single shutdown valve serving both environmental and safety roles, synergetic considerations ensure the most stringent requirement is met. Conclusion: synergetic thinking for real-world protection. Synergetic consequences highlight the interconnected nature of process risks. Ignoring them can lead to under-designed protective functions and underestimated hazards. By formally recognizing compound outcomes in SIL assessments, organizations create more robust, context-aware protection strategies, better aligned with complex operating environments and stakeholder expectations. Process safety time in SIL determination, defining the window for protective action. Process safety time, PST, is the maximum allowable time between the initiation of a hazardous process deviation and the point at which unacceptable consequences will occur. It defines the response window available for an Instrument Protective Function IPF to detect, decide, and act, making it a critical factor in both SIL assignment and system design. Unlike static consequence or likelihood evaluations, PST introduces a time-based constraint. If an IPF cannot respond within the available process safety time, it is functionally ineffective, regardless of its SIL rating or reliability statistics. Key components of process safety time. Initiation point. The moment a deviation begins, e.g. pressure buildup, level rise, temperature increase. Trip point. The threshold at which the IPF should activate to prevent escalation. Response deadline. The point beyond which process conditions become irreversible, unsafe, or destructive. PST is measured from the initiation point to the response deadline, not from when the IPF receives a signal. This includes detection time, signal transmission, logic execution, final element actuation, and process stabilization. Application in IPF design and CL validation. Understanding the PST allows engineers to select appropriate detection technology. For short PST scenarios, fast response transmitters, e.g. for vapor pressure or flow surge, are essential. Evaluate actuator speed and valve stroke times. Final elements must fully close or open within the PST window, including any fail-safe or pressure venting delays. Determine logic solver cycle and scan time. The safety system must process input and output logic without delay that infringes on PST margin. Establish minimum test and diagnostic coverage. Fast-developing HAs require more frequent testing and reliable diagnostics to avoid latent failures. Example overpressure protection in a compressor loop, PST may be 2 seconds from blockage to relief valve damage. High temperature deviation in air reactor, PST could be several minutes before catalyst degradation or runaway. High level in knockout drum, PST depends on inflow rate and vessel geometry, often several minutes. Each scenario must be individually analyzed through process dynamic modeling or empirical data to establish the real PST. Design margin and verification. For the IPF to be considered effective, the total IPF response time must be well within the PST, allowing for margin and tolerances. SIL verification must document that all components from sensor to final element perform within the required time. Design margin, typically 20 to 50%, is recommended to accommodate degradation, variability, or startup conditions. Conclusion: time defines functional viability. Process safety. Time is not just a design parameter, it is a boundary condition for IPF effectiveness. A high SIL function that operates too slowly will fail its purpose. By clearly defining PST and aligning all IPF components to operate within it, engineers ensure that protection is not only reliable but timely, preserving safety and process integrity in real-world conditions.